Today we'll be looking at multiplication of a vector by a scalar. Multiplying a vector by a scalar results in a parallel or collinear vector with a different magnitude. It can also result in a different direction if the scalar is less than 0. So, stating that if k denotes the scalar where k is an element of the real numbers, k times the vector, so the vector v in this case, is equal to k times the vector. And the absolute value of k times our vector v is equal actually just to k times the magnitude of v. So two vectors are collinear if you can find a non-zero vector such that the vector u is equal to our scalar k times our vector v. Just to review, collinear, exists when vectors that lie on the same line or can be translated so they lie on the same line. So therefore, when the scalar k is greater than 1, the vector is lengthened. So it's like it stretches, it's lengthened, and the direction is the same. And the magnitude is just our scalar k times our magnitude of v, our vector. Now when k is between 0 and 1, so therefore when it is a fraction, the vector is shortened. So it's like it's compressed. And our direction is still the same here. And our magnitude, again, is just our scalar k times our vector, our magnitude of our vector here. Also, when k is between -1 and 0, so that means when k is a negative fraction, the vector is still shortened. However, the direction is opposite. And our magnitude is the absolute value of k times our magnitude of our vector. And when k is less than -1, so when, say, it's -2, the vector again is lengthened. It's lengthened just as like when k is greater than 1, so it's lengthened, it's stretched. And the direction also is opposite here. And our magnitude, as above, is the absolute value of our scalar, so k, times our magnitude of our vector v. So also when k is equal to 0, this happens if a vector is multiplied by a scalar of 0. The resultant is always the 0 vector. Recall here the 0 vector is denoted as such. So therefore, if 0 is multiplied by our vector v, we get the 0 vector, not 0. So please note that it has to be equal to the 0 vector. And when k is equal to -1, so this happens if a vector is multiplied by a scalar of -1, the resultant is the same magnitude, however, it's opposite direction. And when k is equal to 1, if the vector is multiplied by a scalar of 1, the resultant is the same vector. and that just comes from our identity property. Okay, so we can move along here. So let's go ahead and look at our distributive property. Our distributive property is the same as when we're using our distributive law when we are distributing into a bracket. So if we have our scalar k multiplied by our vectors a and b, this will just be equal to our scalar k times our vector a plus our scalar k times our vector b. As well, if we have m plus n, okay, times our vector a, this would be equal to m times our vector a plus n times our vector a. So we can use the laws of vector addition and scalar multiplication to simplify vector expressions, so similar to polynomial expressions. So let's go ahead and do so. So we're just going to multiply this 5 by each of the vectors inside the bracket. So we have 5 vector A plus 15 times vector B minus 10 times vector C minus 4 times vector A plus 7 times vector B minus 9 times vector C. Now multiply that 2 into our third bracket, so we get 4 vector A minus 8 vector B plus 12 vector C. And when we collect our like terms, so like terms in this case, remember our like term needs to have the same variables. So in this case, it needs to have the same vectors. So we can add 5 and negative 4 and positive 4. So when we do that, we're going to get this be equal to 5 vector A. Now we can go ahead and look at our B. So we have 15b, 7b, and negative 8b. And when we add and subtract those, we get 14b. And then our last ones are our C's, and we get negative 7c. So that's our simplified form. So now we'll discuss our unit vectors. So unit vectors are vectors of magnitude 1. A unit vector is denoted by a caret. Okay, so it's really important there. Placed over the symbol. Okay, so actually it's placed over the letter. Okay. In order to find a unit vector in the direction of any vector u, we multiply by the scalar 1 over the magnitude of u. So therefore, what that's stating is that the unit vector u is equal to 1 over the magnitude of u times our vector u. So an example of this, if our magnitude of u was 2, okay, so say we have here, okay, and as you can see, our u is as such as our vector. This here, okay, is half of our other u. So our unit vector would be equal to 1/2 times our u. And that 2 there comes from our magnitude of u. So you notice here, we have the same direction, okay, and magnitude of 1. Alright, also any vector u can be expressed as a product of its magnitude u and a unit vector u caret in the direction of u. So what that's saying is if our u caret is equal to 1 over the magnitude of u times our vector u. Then, by cross multiplication, since we can use cross multiplication when we're dealing with an equal sign, our vector u is equal to the u caret times our magnitude of u. So our example here, given that our magnitude of u is equal to 4 and the magnitude of v, of vector v, is 5, and the angle between u and v is 120 degrees, we want to determine the unit vector in the same direction as u plus v. So what we have here, we have our vector u and we have our vector v, okay? And when we know we're adding them, okay, this here will be our u plus v. So as you can see, we can create our parallelogram, okay? We know by our rules of our parallelograms here. So if it tells me that this angle measurement, okay, this angle measurement here, because if we go, this would also be our v. This angle measurement's 120. We know that this angle measurement, all right, is 60 degrees. Along with this angle measurement would also be 60 degrees, and this one here 120 degrees. So we want to determine the unit vector in the same direction. So our first step is to always draw our diagram, okay, with what we're working with. Now our second step, okay, is to find the magnitude of u plus v. So to find the magnitude of u plus v, what we're going to do here is we're going to use our cosine law. So u plus v squared is equal to our magnitude of u squared plus the magnitude of v squared minus 2 times magnitude of u times the magnitude of v cos theta. So let's sub in for what we know. We have 4 squared plus 5 squared minus 2 times 4 times 5 cos, and we have to use our cos 60 because we need to use our acute angle here. So therefore, when we do all of our calculations, and then we take the square root, we're going to take the square root of 21. So that is our u plus v, okay, or magnitude of u plus v. Now our third step here is to actually find our unit vector. Okay, so we're going to let r, okay, denote u plus v in this case. So our r caret is equal to our 1 over u plus v times, our u plus v. So this is equal to our 1 over our magnitude, which we just found in step 2, times our u plus v. And this will be equal to 1 over root 21 times our vector u plus 1 over root 21 times our vector v. So now let's look at our next example here. The vectors a and b are unit vectors. So when they're unit vectors, remember this means that the vectors have a magnitude of 1 that make an angle of 30 degrees with each other. So we want to calculate the value of 2a minus b. So what we have here, we know that the angle between each of them is 30 degrees. So we're going to have, all right, this is going to be our 2a, and we know the magnitude would be 2, since our magnitude of our unit vector is just 1. So if we just had our a, okay, the magnitude of that would just be 1. And this here, because we have minus b, this is going to be our negative b. But our magnitude is always stated as a positive because this is an absolute value, right? So it's equal to 1. So we also know that they make an angle of 30 degrees between the two. Okay, and therefore this is going to be our 2a minus b. Okay, this comes from our triangle law. And then we are going to use our cosine law to find what our magnitude of 2a minus b is. So I'm just going to write this out. Sorry about that, that should be a negative b. And our angle there is our 30 degrees, right? So we can sub in for what we know. So 2 squared plus 1 squared minus 2 times 2 times 1 cos 30. And when we do all of our calculations and take the square root, we're going to get 1.24. So that's the magnitude of 2a minus b. Alright, and the next part we want to determine the direction of 2a minus b. So that's the angle. So when we're trying to find a direction, we're trying to find an angle measurement, and therefore we are going to use our sine law. So when you're finding your magnitude, you're going to use your cosine law like in part A. And when you want to find the direction, so you want to find your angle, we're going to use the sine law. So we have sine 30 over the magnitude of 2a minus b is equal to sine theta. Okay, I should label where theta is. Here is our theta. Okay, because we want to know what direction that value is going in compared to our vector a, all over the magnitude of negative b. So we have sine 30 over, we found the magnitude of 2a minus b, and part A here is 1.24, is equal to sine theta. We know the magnitude of negative b is just 1. So when we do our calculations there, we get that theta is equal to 23.8 degrees. So we can finish this off with a therefore statement. So therefore the magnitude of 2a minus b is 1.24 in magnitude. And direction is 23.8 degrees below A, our vector A, that is. Now our next example. An airplane is flying in the direction of north 30 degrees west at an airspeed of 240 kilometers per hour. The velocity vector for this airplane is represented by our vector v. So what we want to do here, we want to draw a sketch of negative 1/3, so that's our scalar times our vector v, and state the direction of this vector. So let's draw out what we have here. So remember, compass, north, east, south, west, and tells us that we have a direction of north 30 degrees west. So you measure from the north to the west. So we have our vector here, okay, and this here is our 30 degrees. So this is our vector v. Our direction here, okay, it tells us to state our direction. So our direction in this case is north 30 degrees west. Now, when we are looking at the negative is like a reflection. So it's going to be down in our quadrant here. And it's going to be 1/3 of our vector. So this here is negative a third of our vector v. As well as now, we just do the complete reflection, okay? And therefore, this is going to be our new direction. So the direction in this case is south 30 degrees east. So now that is our first part of this example. Now part B, for the vector 3/2 vector v, state its direction and magnitude. So since it is positive, we know it has the same direction, okay, which is north 30 degrees west. Okay, and the second part here, finding our magnitude. Now in this case, we know that 3/2 times our vector v. Okay, we also know from given above that our airspeed is 240 kilometers. So what this is going to be, to find our magnitude, we do 3/2 times our magnitude of v. And we know our magnitude of v is 240 kilometers per hour. So we do 3/2 times 240, and what we're going to get is 360 kilometers per hour. So that is our direction and our magnitude for 3/2 times our vector v. Now in our next example, we want to consider the vector v, whose tail is at -1, 2, and whose tip is at 2, 4. Determine the unit vector v caret. So what we need to do here, we're first going to start off by drawing a x and y axes here, just so we can actually plot our tail and our tip. So we know that our tail is at -1, 2. Okay, so we have a value right here. And we know that our tip is at 2, 4. So from the origin over 2 up 4. Okay, so this here, all right, will be the end, okay, and at our tip. Okay, so we have our vector here, which we can label as our vector v. So what we need to first do is we need to find its magnitude. So what we do to find its magnitude is we look at the distance between the first and second point. So the magnitude of v is just equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So when we sub in our values here, so we have 2 minus -1 squared plus 4 minus -2 squared. So we're going to have 3 squared plus 6 squared. So that's going to be equal to the square root of 45, which is just going to be the square root of 9 times the square root of 5, so it's 3 root 5. So that's our first part. Now we can look at our unit vector. So our unit vector, remember, is just equal to 1 over the magnitude of our vector v times our vector v. So this will just be equal to 1 over 3 root 5 times our vector v. And there's our unit vector. And for our last example here, we want to examine the vectors in our diagram. So we have 3 different vectors, A, B, and C, as you can see to the right hand side. So what we want to do here in part A, we want to express B and C each as a scalar multiple of A. So to be able to do that, our first step is to find what the magnitude of A is. So when we're looking at A here, So what we're going to do is we're going to look at the difference from one point to the next. So the difference between our x's is 1, and the difference between our y's is 2. So we take the square root of 1 squared plus 2 squared, which will just be equal to the root of 5. Similarly, for our vector b, we're going to do the same thing. So if we start our difference between from our tail to our tip, okay, there's a difference of 3. And then for our y's, there is a difference of 6. So this will be the square root of 3 squared plus 6 squared, which is just equal to root 45. But root 45 we know is we can multiply by the square root of 3 times the square root of 5, giving us 3 root 5. Well, look at that. Root 5 is the magnitude of a. So therefore, we can rewrite the vector b as 3 times the magnitude of a. And then let's look at c. So let's find the magnitude of c. So c, the difference in our x's from our tail to our tip, okay, is 2, and in our y's is 4. So we have 2 squared plus 4 squared, which will be equal to the square root of 20. And I know the square root of 4 times the square root of 5 will give me the square root of 20. So I can rewrite as 2 root 5. Fantastic. Again, root 5, all right, is the magnitude of a. So I can therefore state our vector c in terms of a, which a scalar multiple is 2 times our magnitude of a, or sorry, times our vector a. So that is part A. Now in part B, I'm just going to do it above here, just give ourselves a little bit more room. In part B, we want to express a, b, and c, each in terms of the unit vector a caret. So we need to find a caret. Now recall a caret, okay, is just going to be equal to our 1 over our magnitude of a, which is just equal to and multiplied by our vector there, so it's equal to our vector a over root 5, which we can rewrite our vector a in terms of root 5 a caret, okay, just by doing cross multiplication there. So therefore, since we know below here, in part A we found that b is equal to 3 times our vector a, and so we know that b will be equal, or vector b will be equal to 3 root 5 times our unit vector a, so a caret. And we know that our vector c will be equal to 2 root 5 times our a caret. So that's part B. And now in part C, it says determine the direction of vector A. Now remember, when we are determining the direction, we're talking about an angle measurement. So here we have our vector A. We know, okay, by doing this in part A, that we have a difference of 1 and 2. So our rise here is 2, our run is 1. So what we're going to do is we're going to find theta here. So this is actually going to be the measurement according to our x-axis. So we assume this is a 90-degree angle, right? So we're going to use tan theta is equal to 2 over 1. And when we solve this, we get that theta is equal to 63.4 degrees above the x-axis. And that's the end of our lesson.